crossed the 50% mark in the course. We have finished 3 modules and we are into fourth one, which is on regressions and interpolation. Of course, that word sounds very vague right now. What do you know about the word regression? And we'll talk about interpolation later. Maybe that's like the second part of this unit. This is module 4. Any thoughts about the word regression and where you encounter that in daily life?
Going backwards.
Okay, that is the word regression. In a sense, it is correct, but where else do you encounter regressions? Where do you encounter it? Okay, I want some application, like a situation, or how do you use it?
I've heard of interpolation, but I've never even.
So there are other words by other terminologies that are used, one of which is curve fitting. And the other is like modeling. So yeah.
Experiments.
You use this in experiments. For what do you how exactly do you use it? How many of you have done or know the term calibration? What is calibration? Can you tell me? Can you describe the process of calibrating something or the act of calibration?
Ensuring that the measurements for that device are going to be accurate.
It's like zeroing in a machine.
You're all kind of partly right. It is to ensure, but calibration itself is not ensuring. It is to zero it out, but that's not the only thing. In fact, that's not even the part of calibration. That is using the information that you got during calibration to zero out your instrument. What exactly goes on when you say you are going to calibrate an instrument?
Like level out everything, like all the axes, you make sure like it's a.
You are saying the same thing with more words.
You take like a known value.
Okay. A known value, or shall we use the word standard for that?
Yeah.
Okay, and what do you do with the known value? Compare it to? No.
To the accuracy.
Okay, maybe I should give you one specific example. Suppose I have a mass balance. Okay, I'm going to draw a little sketch here. Here's a cage. Here is the pedestal on which you place an item. If you want, I can go get a mass balance from my lab and show it to you. And here is the display. So there is a display here that shows 0.0050 grams or something. Now tell me what exactly is calibration. What is this known value or standard? It could be a little mass that is certified to be 1 gram or 10 grams or half a gram or whatever gram. So let's say we have a standard that is certified to be 1 gram. Okay, you place it on the scale and your output should ideally read 1 gram. But your output may not read 1 gram because of whatever electronic or physical or some kind of wear and tear. Your value could deviate. Let's say it reads 0.9982 grams. Okay, so if I take the known value and say the known value happens to be 1 gram, and my recorded value, or we'll call this instrument response. Instrument response happens to be 0.9982 grams. We'll call this X, usually used to denote something which is independent. And we'll call this Y, usually used to denote something which dependent on X. I'm tasking you with the goal of calibrating this balance in the range of, let's say, 10 milligrams to 10 grams. I'm giving you like a block set which has masses of each known standard value. So you can do this sort of a calibration. And you will produce me a table where it says standard mass in grams and then instrument response or reading also in grams. Okay, so I'll have, let's say, x1, y1, x2, y2, and I'll say xn, yn. This is the process of calibration where you are comparing a known value or a standard with something that you are trying to evaluate. This is the part where it becomes ensuring that it works by checking if it is actually, suppose this instrument were perfect, what will happen? For every known value, you will get almost the same value as the response. If you don't get it, you know your instrument isn't working fine. Okay, and all right, you give me a table of data. What next? How do I use it? So I'm your supervisor. I ask you to calibrate this balance before we use it for a measurement. You get me this table of data. Every time I'm supposed to take this table of data and do a conversion, how do I use this data in a meaningful way? I don't want to walk around carrying all these numbers with me. I want to represent this data in a more compact, succinct form, which involves just a simple equation if possible, and fewer parameters than a list of n. Let's say this n values, let's say like 20. I don't want to walk around with 40 numbers. What do I do?
And like the average and the standard deviation,
Average and standard deviation of what?
like just to see like how plus or minus how well the instrument reads the numbers.
Okay, so you can do that, but not like the way you describe it. Before I say it, anyone wants else to say something?
Take the slope.
Use.
Average slope.
So you from this data, what can you see? What can you see? You can see that y scales with x. Can you? Right? Y can scale with x in an infinite number of ways. Y can increase linearly with respect to x. Y can increase quadratically with respect to x. Y can increase exponentially with respect to x, and you can do this million times. How exactly does y vary with x based on your data? How will you estimate or make that judgment? $75. What are they trying to roast us? All right, I want to say. Okay, I wanted to get you to the point where you can see it is impractical to walk around with tables of data. The act of regression can be loosely defined as, I mean, these are all synonyms, okay? You can use all these three words interchangeably. Is the act of summarizing data sets into functional forms or functions with parameters that are adjusted or selected to capture the underlying trend. So this is a mouthful, but this is what I would call a practical operating definition of what is regression. It is the act of summarizing data sets into functions that have some parameters that can be selected so that the underlying trend is captured. What do I mean by that? Most of this you don't even have to write, I'm telling you, because all of this is going to be on the recording and there is nothing quantitative until I say so, okay? So just listen. So you have this discrete data points which you got from your act of calibration, okay? And now you can see that this y is trending with x, meaning as x increases, y increases. And we just want to start by asking a very simple question. Is y linearly dependent on x? We want to ask a very simple question. And if that is true, wherever x is, suppose you drew a straight line. Suppose you drew a straight line. If all these points fall nearly on that straight line, then the answer is yes. So if you look at a data set, how do you determine if something is changing linearly? Don't go with the pre-assumption that there is an equation or so. All you get is a table of data. From the table of data, how do you figure out if some quantity is changing linearly with respect to the independent variable? Somebody said slope before. I want you to think again about the slope. What is the nature of the slope if for a straight line?
Same thing.
Same at every point, or slope is constant. So you can take the slope between here, or between here, and if you get the same slope every which way, it means the data is roughly linear. Okay, so if it is roughly linear, then you would think an equation y equal to mx plus b would describe your data. Right? That's what a linear data set means. Except m and b are not known. What value would you pick for m and b? Should you pick 0 and 1? Should you pick like a specific value? That you see, there is two steps here. One is picking m and b. Second is getting the best pick. I can just randomly pick a couple of values, a pair of values for m and b. That won't make it correct or the best. If we have to do the best, then we have to figure out what is the constraint or need that must be met so that particular value of m and b which satisfy that need will be the best fit. How do you identify a constraint? How do you identify what is a good fit? What is a bad fit? What is a good fit? What is a bad fit? I'll say it in English. You have to say it in math. Okay. A good fit nearly describes all the data points, and the difference between the fit prediction and the actual data is very small. So if I write that, forget the instrument reading, the calibration, let's just call them with symbols. I have x, x1, x2, x3, xn. Correspondingly, I have y, y1, y2, y3, y. And then I have y fit, which is equal to mx plus b. So I have y fit 1, y fit 2, y fit n. I'm saying in English, the correct best choice for m and b will make sure y fit and y1 are nearly same. Okay, so what is the difference between y fit and y? that is YF1 minus Y1. And instead of calling it fit, I'm just going to add a bar to denote this is fit. So this is Y bar 1, Y bar 2, Y bar n. And I can say this is Y2 bar minus Y2, Yn minus Y. Remember, the best fit leads to the least difference between Yi bar and Yi. So if you pick any one value, suppose you pick this value. Suppose you just take the difference between Y fit and Y for just this value, that doesn't necessarily mean that it will work for everything else. You have to pick something that minimizes the difference, not just for an individual, but for all of them. So what is the difference? This is Y1 bar minus Y1, which could be positive or negative, right? It could, this data point could lie below or above this data point could lie below or above the line. So this difference could either be like this positive difference, or it could be like this negative difference. You with me so far? Okay. So if something can be both negative and positive, how do you get rid of the sign?
Absolute.
Absolute value is one way of doing it. We can also square it and add it. You can square it and add it, right? So let's define this difference. We'll call it epsilon. This is Y1 bar minus Y1 squared plus Y2 bar minus Y2 squared plus and so on, Yn bar minus Yn squared. Okay. Our simple constraint is the fit parameters M and B must be chosen such that epsilon is a minimum. It will lead to the least possible value of epsilon, the square of the differences. With me so far? And how do you ensure that? If something is a minimum, we know that the derivative with respect to M must be 0 and the derivative with respect to B must also be 0. Right? I mean, if this is just calculus. If this epsilon depends on two parameters and it reaches a minimum, which means that epsilon, the slope at that point with respect to M and with respect to B must be 0. What is this? This is like writing partial over partial M summation I runs from 1 to n y I bar minus yi whole squared equal to 0 and partial over partial b I equal to 1 to n yi bar minus yi squared equal to 0. What is yi bar? What is yi bar? This is nothing but m times xi plus b. This is the idea of a linear fit, right? That is, instead of carrying around the original data, all you need to carry around is this equation and the range of x. X varies between x1 to xn. This simple equation summarizes the entire data set. Summarizes or accurately represents the entire data set xi, yi, where I runs from 1 to n. So wherever yi bar appears, replace it with mxi plus b, and let's do this math. Okay, it's actually not all complicated. Remember, this is the starting point of our discussion. The best fit leads to least difference. So we are minimizing the difference. Okay. So let's do some algebra here. Partial over partial m, sigma I equal to 1 to n, m xi plus b minus yi squared equal to 0. This is derivative of a sum, which you can write is the sum of a derivative. All I have to do, this is all linear, right? So this is like n terms, term I equal to 1, I equal to 2, and so on. So I'm going to write this is I equal to 1 to n, partial over partial m, mxi plus b minus yi squared equal to 0. Can you do this differentiation? That will be 2 times mxi plus b minus yi times m summation I equal to 1 to n equal to 0. Are you okay?
Oh, yeah, I'm trying to remember the partial differential with the in the xi. Why is the m and not
This one. So this is like differentiating 2m of, let's say, m squared. This is 2m. So instead of m, I have m inside a function. So I have 2 times that function. Then I have to differentiate what is inside. These don't depend on m. This depends, sorry, this has to be xi. My bad. Thank you. Okay, so you have this. This is like writing, forget the 2 because 2 is not equal to 0. You can cancel it on from every term. So this is summation I equal to 1 to n m times xi squared plus summation I equal to 1 to n b times xi, and this is equal to summation I equal to 1 to n xi yi. Look at this and tell me this makes sense to you. If it doesn't, I can explain a little more. All I did was to multiply the xi and split the sum of a polynomial into 3 terms. That's it. Are we okay? This is good. You are able to follow? So, what is this? M is a constant, right? I can write this summation sigma I equal to 1 to n xi squared plus b times sigma xi equal to sigma xi yi. M and B are not known. They are the values we are solving for. What about this? What about this? What about this? Are these known or unknowns?
Assuming we have a table.
You have a table of x and y values, which is your starting data. If you know the list of x and the corresponding values of y, you can get sigma x, can't you? All you have to do is do a summation of all the x values. Right? And what is sigma xi squared? Just take whatever x is, square it, and then sum it. Again, something you could do. What is xi yi? Take x, take y, multiply them, and then do the summation. So these three quantities are coming directly from your raw data. We are going to, in a minute, we are going to do this on Excel, where you're going to automate it and get these summations like this. Okay, so this is equation 1, which has m and b, and these are the coefficients. I might as well call it alpha m plus beta b equal to gamma. Right? These are all constants. What about the other equation? To solve for two variables, you need two equations, right? So take the other one. You start similarly, partial b summation yi minus yi bar minus yi squared equal to 0, which implies summation partial derivative with respect to b m xi plus b minus yi squared equal to 0, and this would mean summation 2 times mxi plus b minus yi times nothing, I equal to 1 to n is equal to 0, which means for the 2 m times sigma xi plus b times sigma 1 equal to sigma yi. Sigma xi, you just sum up everything. What is sigma of 1? Counting 1 n times. Like it's basically the number of entries in your data. It's like a clicker for each row. So this is basically n. And then what is sigma y? Just sum the y column. So you have your second equation, which is m times sigma xi plus b times n equal to sigma yi. Two equations, two unknowns. Did we see solving these side of linear equations in the first unit or second unit? Right? Two equations, two unknowns. You can use Cramer's rule or your method of choice. Okay? All right. So note down this up to here, and now we'll do this as an example problem. First, we can do this by hand and then by Excel. Okay? All right. I'm going to pick one problem from the book. Problem 17.3, I'll write down the data so that you can actually try this. Maybe should I wait for 30 more seconds? People are still writing. Are you writing? Good, good, good. So in the exam or when you do problem solving or curve fitting, you don't have to go through all these derivations every time. All you have to know is this equation and this equation in order to do linear fitting. Okay, so let's start with the data. This is problem 17.3. Here is x, here is y. X, y. 0, 5, 2, 6, 4, 7, 6, 6, 9, 9, 11, 8, 12, 7, 15, 10, 17, 12, 19, 12. This is your data. Once we set up the equation, let's use Excel to do this. So if you have your computer, you might start entering this in Excel. Okay. In fact, in the exam, what I would do is I would actually give you sigma x, or let's say I have a column for x squared, I have a column for xy, I'll provide all these values to you. You don't have to do any of these calculations, but what I won't be telling you is how to use them. So where do you start? You write down this equation first to solve for m and b. Our first equation is sigma m xi squared plus b times sigma x equal to sigma xi yi. Then m times sigma xi plus b times n equal to sigma y. Need the following: sigma xi squared, sigma yi, sigma xi yi. Get out your Excel and enter this and compute the remainder. So I want you to tell me these four values, okay, so that you can put it in here. 5 minutes. We'll meet again after 5 minutes. Are you getting values? Are you getting these values? Yes. In more, I mean, of course, it's easy to get this, but I want you to get the process. Okay. So our equation to solve would be 95m plus, sorry, not 95m, 1277m plus 95b equal to 911, and then you have 95m plus 10b equal to 82. I want confirmation from each of you that you are able to get all these values. I know some of you said yes. Are you working on this? You got it? Okay, good. Mary, working on this? Something not clear? Yeah, watch the video, please. Okay, all right, so you have two equations in two unknowns. You can solve anyway. Let's do Gauss elimination, which is simpler. So B is 82 minus 95m divided by 10. Or I'll write it simply 8.2 minus 9.5m, which I can substitute 1277m plus 95 times 8.2 minus 9.5m equal to 911. You can rearrange this and tell me m would be 911 minus 95 times 8.2 divided by 1277 minus 95 times 9.5. And what will that be? P would be 8.2 minus 9.5 times 0.3543 would be Are you getting these values for slightly different, like differing the third or fourth decimal, or okay. Okay, 1 second. I'm going to bring up my screen here. Okay. If you're trying or if you're finished, please take a break. I want to show you some results from the Excel calculation. Okay. So take a break, look up. Okay. So here is the data, X and Y. And if I'm in the exam with you, I would use my Excel if I'm allowed to calculate X squared, XY. And from that, I would calculate my M and B values. Okay. So M happens to be 0.35 something and B is 4.85 something. Okay. So what I did was to take these M and B values and calculate Y fit. What is Y fit? Y fit is mx plus b. M times x plus b. So I got my Y fit for each value. First thing I want you to do is to compare Y fit with the corresponding true value of Y. This is your raw data. This is the approximation to your raw data. You get 5 and in the raw data, you get 4.85. So that's a difference of 0.15. 6, 5.55. 7, 6.26. 6, 6.96. 8, I'm sorry, 9, 8.02. What are you seeing here? There are significant differences. Okay. So let's go and plot our data. Okay. Here is a plot of the original data, Y and X. Okay. To this, I want to add my fit line. I can do it two ways. In Excel, I can just select and say add a trend line, and my trend is linear. Okay. So I can just ask it to display the equation. All right. So this is the fit that Excel's algorithm produces 0.3525, 4.85, sorry, 4.8515. Very similar to the values that we got. If you round it to 4 places, this is also the same. Okay. Notice from the graph that there is a population of particles, I'm sorry, population of points, some of which are above and some of which are below the line, the fit line. The fit does not or will not explain every data point. That's the first thing you got to remember. It won't pass through every data point, which can't then be a straight line. If it passes through every little point, then it can't be a straight line. In order to have a linear fit or a linear trend, what this means is, on an average, it describes the variation in Y with respect to X. It doesn't explain the variation of every single point, but rather the entire population or entire set. Okay. Now, if I also take the error value. What is error? Error is my original data minus the approximated fit. I compute that error, and now I'm going to plot the error as a function of X. So I'm going to plot these two columns. Oops. All right. So let me adjust this axis. All right. All right. So are you seeing these tiny points? Right. So the attribute of a good fit is that it captures the trend in the data and does so without any bias. So if you plot the difference between the fit and the original data as a function of X, how will you recognize bias? What is bias? Favoritism towards one side. There are only two sides here. Either the error can be more negative or the error can be more positive. A good choice for M and B will make it equally likely to have a negative error and a positive error. So if you have, say, 10 data points, you should roughly have 5 with positive error and 5 with negative error. Or if you add up all the error values, they should roughly add up to 0. they should roughly add up to 0. That would make this a unbiased fit. How do you visually recognize this? If you are seeing this graph, what will you look for to say this is biased towards one side or the other? If suppose all the error values are positive, or nearly all of them are positive and only few of them are negative, or the other way, that would be an example of a biased fit which doesn't capture the data very well. It is systematically under or over predicting. Okay, so once you do the fit, the problem just doesn't end there. You have to plot it to see if your fit is an unbiased representation of your data. And you do that by visually inspecting. Okay, there are also mathematically quantities that you can calculate, but as beginners, I want you to have that intuitive sense. Okay. All right. Questions?
I get the process.
Hmm.
I guess what is the importance of like the error being positive and negative in a way? Like,
Good question. We'll come back to a calibration example. I'm giving you a mass balance and a set of standard weights and asking you to come back with the calibration. You produce the data, okay, and there can be two sources of error. One is your instrument is faulty. The other is you, the person doing the analysis, made mistakes. Suppose the instrument is fine. Instead of choosing the best possible values for M and B, you chose a value somewhat arbitrarily, which always said when the true weight is 1 gram, the reading happens to be 1.2. It somehow gets that bias built in. That is, what is the consequence of that? If I'm going to take your calibration and use it as part of a calculation, I am introducing error because you introduced bias. So the importance of excluding bias comes back to accuracy. Remember in our very first lecture, we talked about the gun range and had bias versus precision. Accuracy versus precision. You want to be precise. You also want to be accurate. Bias basically kills accuracy. Okay. So any data that you generate or handle, you want to summarize it in an unbiased fit so that it is accurate moving forward. Remember, suppose this is only 10 data points. Suppose you had 100,000 data points and you represent that with a linear fit, you are still reducing 100,000 numbers into two numbers. So you want to make sure that two numbers capture the trend accurately for the entire 100,000. So that moving forward, your assumptions or calculations based on your fit are just as good if you had used the entire data set. Okay. So you did a vanilla linear fit now. You have now learned the technique of doing linear fit. With that linear fit, there is so much more we can do. Shall we try the next variant of this? So one equation to remember or to put down on your sheet, tell that right now. Is this equation. This, if you know, or whenever I say linear fit, you are able to start here. That means you have understood the steps before that. Okay, so let's keep this. Let's look at different data sets and try to do some examples. Okay, we have half an hour, so maybe 2 examples. Let's do problem 17.8. If you have your textbook with you, problem 17.8. Problem 17.8. problem 17.8. I'm going to write it down. X, Y. You might as well enter this in your Excel if you want. 2.5, 13, 3.5, 11, 5, 8.5, 6, 8.2, 7.5, 7, 10, 6.2, 12.5, 5.2, 15, 4. 19.1, 4.6, 20, 4. Either I'll provide the sigma x, sigma y to you, or I'll let you bring your Excel to Excel. Either way, I don't want you to do hand count. Now, before you begin, your goal is to fit a regression to this data. Can we first check if this data is linear at all? How do you check for linearity? The slope at any calculated in any way, if it's linear, it will match. So let's calculate what's the slope based on these 2 points. 13 minus 11 divided by 3.5 minus 2.5, or this is 2. Okay, the slope based on the first 2 points is 2. Let's pick any other 2 points. Let's pick these 2 points. You have 6, should do it the other way. 11 minus 13, which will make this minus 2. 5.2 minus 6.2 divided by 12.5 minus 10, which is minus 1 divided by 2.5. This is 0.4 or minus 0.4. Yikes. Slope is not constant. So no longer a linear data. Okay. You can check one more point. Maybe you can take these two. 8.2 minus 8.5 divided by 6 minus 5, which is minus 1/3 or minus 0.33. Not a linear trend. Not a linear trend. Everybody is on board with that? Okay. So we learned one trick, right? We want to extract maximum utility out of that one trick. So the way to extend its utility is to think about the concept. Can we linearize the data by not plotting x versus y, but x versus something else, or by plotting either say x versus log y or log x versus log y or log x versus y. Essentially, we are trying to ask, is the data linear if plotted on a semi-log or log-log basis? That's the question we are asking. Okay. Of course, getting the log of these quantities can be messy. So now we are going to switch to Excel if you are done writing. So if you are using your Excel, go ahead and calculate logarithm of x and check if this data is at least linear if you consider y and logarithm of x. Let me see if you can understand what I'm asking you to do. I'm going to enter this data in my Excel. So I have. Are we all done writing here? Can I pull down the screen? Okay. Okay. Okay, so take a pause, look at the screen. We'll do some talking and then I'll give you time to finish this. So here is x versus y, okay? If I just took x versus y and plotted the data, you tell me, does this look linear to you? No, of course not, right? Initially the slope is very high and then the slope almost becomes flat. Do you recognize any other function that could potentially fit this data? Any other parameter or function that could represent this data? We'll see that, okay? We'll see how we can arrive at that even without knowing beforehand. All right, so the only thing I'm going to teach you first is that get the logarithm, okay? We'll call uppercase x equal to the natural log of x and uppercase y is the natural log of y. So we'll take this. I don't deal with logarithm with respect to 10. So if I say log, I mean natural log, okay? You don't have to follow through right away. Just listen because I'm going to show you a trick, okay? All right, you have logarithm of x and logarithm of y. Let us check if these two trend with each other linearly. Okay, so I'll give you time to do this. Okay, so instead of plotting x and y, I'm going to plot logarithm of y and x to see if that would trend linearly. Does this is the plot of log y versus x. Does it look linear to you? Still not linear, right? So what if we took logarithm of x and plot it against logarithm of y? Does this look linear to you? This looks reasonably linear, right? And how do we check? We can go back here and compute the slope between any 2 points and see if the slope is roughly the same. Okay, so minus 0.5, if I put it anywhere else, it does change a little bit. Okay. All right. So it does change around, but not as drastically as before. Okay. So what we are going to do, I want you to treat, instead of the original data, treat the logarithm of x as your x variable and logarithm of y as your y variable and do the fitting on this column instead of the original data, the transformed data instead of the original data. So if you call this x, what is our equation behind the screen? Do you remember that? That is m times sigma x squared plus b times sigma x uppercase equal to sigma xy, and then m times sigma x plus b times n equal to sigma y. Now your uppercase x is column C, uppercase y is column y. The rest of the process is just the same. Do that. Get me m and b values and then we'll talk. Can you? Can you try? Those who are trying. Question? No? So what is sigma x squared? Okay, before you do that, is everybody clear with this equation? This is the one we have been deriving since morning. Okay, so now let's get the necessary quantities. Okay, I'm going to write x squared, xy. What is x squared? I need to take the square of this. What is xy? I need to take the product of this. Okay, all right. So I need the sum of all these. Sum. So we got a data set and then we did logarithm of the data set to get a transform data and we are fitting the transform data. Okay. So you have these quantities. How will you now get the m and b values? Give you a few minutes to get up to here and tell me, and then we'll proceed. Yes. Oh, sorry. I mistakenly squared the sum of x. What I should have done is summed x squared. So I should write equal to sum of this column. Instead, I just took this value and squared it, which is obviously wrong. So I should do, yep. Over the years, I do make a lot of mistakes. I do bumble my way through this. And when students fix it, I know they are getting it. Are you getting these values? Yes? Yes? Why?
Yeah.
Yeah, everybody's here. Okay, so now all you need to do is, let me switch this off. You have your Excel in front of you and you are trying to treat, instead of using the symbol small x, we'll use the symbol uppercase X. xi, yi, yi, xi. And what is uppercase X and uppercase Y? Uppercase X is natural log of X and uppercase Y is natural log of Y. Right? So with the values that you do have in front of you, can you go ahead and solve for M and B? So this is sigma X is 20 point sigma xi is 20 point. Can somebody tell me? 9795. Sigma xi squared is 48.4509. Sigma yi is 19.1795. And sigma xi is 37.8401. So with these values plugged in here, I will not do this. You do this and tell me what are M and B values. Do you have a value?
Yes.
Tell me.
For M, I know 0.703058.
7031.
Yeah.
Okay, and for B,
Negative 0.18.
18. Is anyone else getting similar or different values? Tell me. For M, negative 1.6681. 4175. Okay, we have two candidates. Any more? So this table of data, okay, and this information plus the information where you get sigma x and sigma y for the original variables, everything will be provided to you and you have to pick the needle from the haystack. If you don't know what you're doing, you don't know which summation to use, having the summation isn't of any use to you if you don't know what to do with it. Anyone else? Do you have a value? No. So my Excel says the value of M is minus 0.5403 and the value of B is 3.0514. That is, I didn't do it, Excel did. I just used the regression fit in there to tell me the fit constant still. I mean, if you are allowed to use Excel, you would still go through these calculations and you can try to get M and B quickly, right? So just to make sure we are all doing the same equation, 48.4509 M plus 20.9795 B equal to 37.8401. And then I have 20.9795 M plus 10 B equal to sigma Y being 19.1795. Tell me if this is the equation you are trying to solve. You are getting this?
Yeah.
Okay, so you can check these later, but this should be correct because I mean obviously multiple people are getting this. All right, now drop your pencil, listen. What does this M and B value mean? Y equal to minus 0.5403 times X plus 3.0514. Okay. For simplicity, I'll just write this is mx plus b, y equal to mx plus b. But what is uppercase X and uppercase Y? They are the logarithm of the original data, right? This is logarithm of Y equal to m times logarithm of X plus b. You're with me? I just put back the original definition. Original definition of Y and X. You look at this equation, how will you rearrange this? You know about logarithms, right? Can I write this logarithm of Y equal to logarithm of X power M plus B? Can I write this? M log X is logarithm of X power M, right? And I can write this logarithm of Y divided by X power M equal to B. Can I? Yes or no? And if I take the anti-logarithm on both sides, I'm going to get Y over X power M equal to exponent of B, or Y equal to exponent of B times X power M. Okay, I'll give a new name for exponent of B. I'll call it like uppercase B. So Y equal to B X power M is the fit for the original data. So in the exam, you will be given a table of data and asked to come up with a linear fit for the data, and that's it. I won't tell you whether you should do logarithm, whether you should do linear. I will tell nothing. You are supposed to try different things and come up with this final form. Okay. So this process, does it make sense to you? The linear fit that you did is between the transformed variables. I'll write it here. Linear fit between transformed variables. You start with that linear fit by applying the original definition. Applying the original definition of uppercase X and uppercase Y. X and Y. You start here, you work backwards to bring it in terms of Y equal to some function of X, which happens to be a power law. This is called a power law. Questions? Like, I'm not clear, question or comment or clarification? And how you get good at this transformation business is by doing more examples. I did just 2 examples, one with the regular linear fit and one with a transformed linear fit. You just do more examples in them. Okay. Okay, we have 5 minutes. So next lecture we'll try to do more examples on this. Okay, I want to leave with one concept here. We can do that right now. Okay, let's do that right now. Actually, that will be a better use of the time than starting a new concept. So here is our data. Okay, let me screen share this. All right. So here is Y fit. What is Y fit? Y fit is minus 0.5403 times uppercase X plus 3.0514. Okay, I can calculate all the Y values here. And error, which is defined as Y fit minus Y, that would be this column minus this column. Okay. And our transformed variable, that is the original data, we wrote y of x is equal to exponent of b times x power m. That is our original fit. Okay, that would be exponent of 3. What is the value? 0.0514 times x, which is right over here, power minus 0.5403. And the error of this fit would be y fit minus y, which is this minus 13. All right, so couple more minutes. Look at the column B. Y values are 13, 11, 8.5, 8.2, and so on. Look at column J. 12.88, 10.74, 8.86, 8.03. You can see that it follows the data pretty closely. And if you compute the error is a small number, but it is also generally symmetric about 0, which makes it a good fit or unbiased fit. So you can from here quantify what is the total error. That is, if I say error squared, that is this squared, and I'm going to compute it for each row, and then sum of the error squared. Sum of the error squared. This quantity here, what was our original goal? It is to make that quantity as small as possible. You can't make it 0, but we settle for the next best thing. Okay, so this is the sum of the error. Error is defined as y fit minus y. And here's a question for you. If you had, we have only 10 data points here. Okay, suppose you had 200,000 data points. Will this number grow bigger with the system size, or will this always be the same or small value? This summation of error squared, will it grow with the system size, or will it just be the same value for any size, any population size? If I had 20 more rows, each row will contribute a value like this. So it is sort of meaningless to compare this number, but you have to divide that by the number of data points, right? Like you have to average it. So we are going to take this value, okay, we'll call this S summation R, summation of error for regression, and then we'll take this value and divide it by the number of data points minus 2, which is related to the degrees of freedom, and then we'll define a standard deviation, which is square root of this. This 0.20 you see here is normalized for the size of the data set, and we can use this to do some statistical estimate of the accuracy of your fitting. That part will continue in the next lecture. So far what I did was to get the error squared, sum it up, and from next lecture we'll pick it up here. Okay, so like it's not just that you do a fit and be done with it, you have to also say statistically what is the accuracy of that fit. That part we'll do first thing next lecture. I'll post this file on the canvas. Thank you.